to the second episode of Einstein's Entanglement, a short video series based on the book Einstein's Entanglement, Bell Inequalities, Relativity in the Qubit, published in 2024 by Oxford University Press. I'm your host and co-author of the book, Professor Stuckey. You can see that the book has endorsements from some highly regarded members of the Quantum Foundation's community, so you can rest assured that what I'm explaining to you in this video series is acceptable physics. In this episode, I will introduce the greatest mystery in physics, quantum entanglement, that has led to a decades-old quagmire in quantum foundations. To introduce the mystery of Einstein's entanglement, I'll use David Mermin's famous paper, Bringing Home the Atomic World, Quantum Mysteries for Anybody, that Richard Feynman called one of the most beautiful papers in physics that I know. Merman introduces the mystery of Einstein's entanglement using his Merman device shown here. You don't have to know anything about quantum mechanics to understand the mystery using this device. So his paper allows him to convey the mystery of quantum entanglement to the general reader. At the very end of his paper, he challenges the physicist reader to solve the mystery in a way that the general reader can understand. No one to date has successfully answered Merman's challenge without using spooky actions at a distance, or causes from the future, or conspiratorial control over experimental procedures, or infinitely many realities, or some other crazy idea that has been around for decades without garnering consensus support. That's the quagmire of quantum foundations. Now, let me explain how the Merman device works. The device has a source of two particles. That's the middle box of the picture. And the two particles are sent to and measured by the two detectors in one of three settings, 1, 2, or 3, as shown in the picture. There are two possible outcomes in each trial of the experiment, R for red or G for green, as indicated by the lights on the top of each detector. Let Alice and Bob be the people making the two measurements. If the particles simply generate R or G outcomes randomly at each detector in each trial of the experiment, and Alice and Bob are randomly selecting the detector settings, these are the outcomes we would see. There are three ways that Alice and Bob can choose the same settings. Alice chooses setting 1 and Bob chooses setting 1, or 1, 1 for short. Alice chooses 2 and Bob chooses 2, or 2, 2 for short. Alice chooses 3 and Bob chooses 3, or 3, 3 for short. Merman calls this case A. That leaves 6 ways they can choose different settings. Merman's case B. That is 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. Don't worry if you didn't follow it. Just realize that this is the table of results for the random case, and it's not what the Merman device for quantum mechanics produces. Here is what the Merman device, or quantum mechanics, produces. Fact 1 is that when Alice and Bob happen to choose the same detector settings, case A, they always get the same color outcome. Half the time both are red, RR, and half the time both are green, GG. Fact 2 is that Alice and Bob only get the same color outcomes in 1/4 of the trials when they happen to choose different detector settings. That's case B. 1/8 of the time, both are red, and 1/8 of the time, both are green. So what's so mysterious about that? Let's start with fact 1 about case A. Merman writes, why do the detectors always flash the same colors when the switches are in the same positions? Since the two detectors are unconnected, there is no way for one to know that the switch on the other is set in the same position as its own. The particle properties must be coordinated in some way so as to produce the same outcomes for the same setting numbers when interacting with the detectors in each trial. He calls the hidden deterministic particle properties instruction sets and writes, it cannot be proved that there is no other way, but I challenge the reader to suggest any. Now, in answering Merman's challenge, the particles cannot know how they will be measured until they arrive at their respective detectors. This is called statistical independence. Also, Alice's particle cannot know how Bob's particle was measured before it renders an outcome at Alice's detector, and vice versa. This is called locality. Retrocausality, with its backward in time causal influences, violates statistical independence, and Bohmian mechanics, with its faster-than-light pilot wave, violates locality. Merman prohibits violations of locality or statistical independence in answering his challenge. So let's see what happens when we assume instruction sets are responsible for the Merman device outcomes. You can see that fact 1 about case A is satisfied. No surprise there, that's why we invoked instruction sets. But you can see that instruction sets do not reproduce fact 2 about case B. Fact 2 says only 1/4 of the case B trials will be the same color, but instruction sets give us the same colors in 1/2 of the case B trials. That's the mystery of Einstein's entanglement. It's very easy to explain the greatest mystery in physics to a general reader, but Merman's challenge is still unanswered. Well, except for the information theoretic or principal answer we will provide in episode 4. Lest you think this is all hypothetical, the 2022 Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for doing entanglement experiments and verifying the mysterious quantum mechanical predictions. Let me show you a popular physical instantiation of the Merman device using a property of electrons called spin. It's a sort of internal angular momentum, like the rotational angular momentum of the Earth as it spins on its axis. Up, down. Turns out that's a bad analogy, but it's a picture for you to have in your head. Anyway, as Stern and Gerlach sent silver atoms through a non-uniform magnetic field, they found the atoms were deflected up towards the north magnetic pole or down towards the south magnetic pole, never anywhere in between. The deflection was eventually attributed to the spin angular momentum of the silver atom's valence electron, which equals plus or minus Planck's constant h divided by 4 pi. So, as Steven Weinberg pointed out, when you measure electron spin with Stern-Gerlach magnets, you're measuring Planck's constant h. What's true about such measurements is that the electrons are always deflected the same amount up or down relative to the north-south magnetic poles for a particular source, no matter which way the Stern-Gerlach magnets are oriented or aligned in space. We can restate that as an experimentally motivated postulate, like the light postulate, as follows. Everyone measures the same value for Planck's constant h, regardless of how they are oriented in space. Now, this is not what we expect from classical physics, where the silver atoms are coming out of the source with all possible orientations of their magnetic dipoles, as in this picture of the Stern-Gerlach experiment in Randy Knight's Intro Physics textbook. So we see we can attribute the quantum property of spin angular momentum to the observer independence of h. Now we consider Alice and Bob making Stern-Gerlach spin measurements on a pair of spin-entangled particles in different directions. Then we restrict Alice and Bob's Stern-Gerlach magnet orientations to these 3 directions. Finally, let a red outcome on the Merman device detector correspond to a +1 spin measurement outcome. Green correspond to a -1 spin measurement outcome. Same Merman device setting numbers means theta equals 0 between Alice and Bob's Stern-Gerlach magnet orientations. And different Merman device setting numbers means theta equals 120 degrees. In this case, the Hilbert space formalism of quantum mechanics gives these joint probabilities, which exactly reproduce facts 1 and 2 for cases A and B respectively. This is what Merman called the elementary quantum mechanical reconciliation of cases A and B. In order to successfully answer Merman's challenge, you would need to derive these joint probabilities without using spooky actions at a distance, as in Bohmian mechanics, or causal influences from the future creating effects in the present, called retrocausality, or conspiratorial causal control of experimental procedures, called superdeterminism. Okay, so here's the result of a 2025 survey by editors at the journal Nature, in which 1,101 researchers in quantum foundations, and myself included, said which interpretation of quantum mechanics they preferred. As you can see, the results are all over the board. The most popular, at 36%, is the Copenhagen interpretation that Merman called shut up and calculate, because it doesn't tell us how quantum entanglement works, nor does it tell us why quantum entanglement exists at all. Essentially, the Copenhagen interpretation says, the formalism of quantum mechanics maps to experimental outcomes nicely. What else do you want? And this is the quagmire of quantum foundations. Chris Fuchs sums it up nicely. What is the cause of this year after year sacrifice to the great mystery? Whatever it is, it cannot be for want of a self-ordained solution. Go to any meeting, and it is like being in a holy city in great tumult. You will find all the religions with all the priests pitted in holy war. They all declare to see the light, the ultimate light. Each tells us that if we will accept their solution as our Savior, then we too will see the light. And Tim Maudlin echoes that. They may correctly note that according to every one of their rival theories, God was malicious, and having thus eliminated every other possibility, claimed their own theory the victor. The problem is that every partisan can argue in this way, since every theory posits some funny business on the part of the deity. In the next episode, episode 3, I will introduce a similar situation that existed in physics in the late 1800s and explain how Einstein solved that mystery by avoiding causal mechanisms altogether. In perhaps the greatest irony of physics, as I will explain in episode 4, it is precisely Einstein's principal approach that quantum information theorists copied to solve the mystery of Einstein's entanglement.